So we're trying to prove that the set G mod n, which is the set of left cosets of n, is a group, right? Where n in G is a normal subgroup. So we've defined a law of composition, which is that so we take the coset an, and we want to define the law of composition with the coset bn. Say a and b are elements of G. These are two cosets, and this is equal to ab times n. Right? I guess I'm using star for the law of composition here. Maybe I could. I don't need to if I don't want to, but I want to, because just to make that clear. But so yeah. So the point is that we have the law of composition. Now we need to show that this is going to make this set into a group. But what we can, and so the way that we're going to do this is by using homomorphism, except that we kind of can't use a homomorphism because we don't know this is a group, so we can't use group homomorphisms. So we'll do it in a little bit of a roundabout way. So we already know we have the map, the projection map, G to G mod n, which takes any element G to its left coset, Gn, right? And because the cosets form a partition, we have that this is going to be surjective. So this is a surjective map. And now what we've shown here is that P of A times B, which is, AN, BN, well, that's ABN, so that's equal to P of, well, actually, I did this wrong, didn't I? I should have written it this way. P of AB is ABN, because that's what the definition of P is, right? You take whatever's here and you stick it next to N to make its own coset. But this happens to be the same set as this, which is also a coset. So you can write it this way, and so this is the same as P of A times P of B. So this is the condition we would have for a homomorphism. The only thing that's wrong with saying that this is a homomorphism is the fact that we don't know that G mod n is a group. So what we're going to do is we're going to prove the following lemma. And this is how the lemma is going to go. So if G is a group, and then let's say Y is a set, and then we have a map phi from G to Y, which is surjective. It's a surjective map, and phi of A B equals phi of A times phi of B, in the sense that, so let's see. So Y is a set, but I guess I need to say that Y is a set with a law of composition. So let's see. Really what I should say is that I've missed an assumption. So Y is a set with a law of composition. So Y is a set that looks like a group, right? It sort of almost looks like a group, it's got a law of composition, but we haven't yet verified the axioms for y. So that's what this lemma is about. It's, we have a set that it has a law of composition, right? So law of composition is a map y cross y to y. And then we have this surjective map from G to Y with this property. And so this is the law of composition in Y. And of course, multiplication here is just going on in G. So then we'll get, then the conclusion is going to be that Y is a group and phi is a homomorphism. And so the proof of this is really, so okay, maybe I'm not gonna quite do the whole proof, but the idea of the proof is to carry the group axioms over from G, big G. Carry the group axioms over from big G, right? So we have, 3 axioms: associativity, identity, and inverses. Right, so how would this look, right? So let me talk about identity for a second. So we have an identity 1 in G. So then we'll define 1 y to be phi of 1, phi of 1, phi of 1. This letter can be phi or phi. It's either way. So 1, we'll define 1, we'll define the identity to be phi of 1, and then, so then for any, for any x and y, or maybe I should say little y and y, and for any little y and y, well, first of all, little y is equal to 5 something, and let's call that something a, and then, so 1y times y, well, that's equal to phi of 1 times phi of a, which is equal to phi of 1 times a, which is equal to phi of a, which is y. Right, so that's the part of the identity axiom that 1 times y equals y. And then, so of course you would do, to fully verify the identity axiom, you would do the same thing for, y times 1 y. You can, and of course the proof will be, pretty much exactly the same as this right here. And, you can do inverses kind of the same way, right? You'll define y inverse. Well, so y will be equal to phi of a, and y inverse will be phi of a inverse. And then the homomorphism property will get you, all of the axioms that you need, because G is a group, and because because the map is going to be surjective. Associativity will also follow in a similar way. That proof is going to be way longer, so maybe I won't say anything about it. But so if you aren't completely sure, this is an exercise for you, is to finish this proof by going through the axioms and carrying over each one of them to the set Y from the set G. Right, we're carrying them from G to Y, And so in particular, you should do the identity axiom and the inverses axiom first, because associativity is a lot of trouble. So if you can understand what's going on by just doing these two, that's fine. Or just do associativity. I don't know. Maybe you're not afraid to write down. Okay. Anyways.